Welcome to this lecture on the average sample number function, a crucial concept in multivariate analysis and non-parametric methods. Imagine you are a quality inspector testing a batch of light bulbs. Instead of testing a fixed number of bulbs, you test them one by one, stopping as soon as you have enough evidence. This sequential approach saves time and resources. Today, we will explore how to calculate the expected number of observations required to make a decision using the average sample number function. Let us dive in. Now that we understand the basic premise, let us look at how sequential analysis differs from traditional statistics. In a standard test, you decide on a fixed sample size before you even begin. However, in a sequential probability ratio test, you evaluate data one observation at a time. After each piece of data, you make a choice: accept the hypothesis, reject it, or continue testing. Because you stop exactly when you have enough evidence, the total number of samples you end up taking is not fixed. It is a random variable, which we call n. The average sample number, or ASN, is simply the mathematical expected value of this random variable given the true population parameter theta. To find a mathematical formula for the average sample number, we must rely on a fundamental theorem known as Wald's equation. In our sequential test, we calculate a value called the log likelihood ratio for every single observation. This ratio measures whether a piece of data supports our first hypothesis or our second hypothesis more strongly. We keep adding these individual ratios together until the total sum crosses a specific boundary, at which point we stop. Wald's equation connects the expected value of this final cumulative sum to the expected value of the sample size. If the individual pieces of evidence strongly support one hypothesis, the individual ratios will be larger, meaning the cumulative sum reaches the boundary much faster, decreasing the total number of samples needed. This formula we just saw leads us to the fundamental equation for the average sample number. By substituting the expected boundaries into Wald's equation, we get this result. The numerator represents the expected final value of our cumulative sum. It is a weighted average of the lower boundary B and the upper boundary A, based on the probability of reaching them. The denominator is the expected amount of evidence we gather from a single observation. In plain English, this formula says that the average number of steps you need to take is equal to the total distance you expect to travel, divided by the average distance you travel in a single step. If you increase the expected evidence per step, the total number of samples required will naturally decrease. Now that we have our formula, let us understand how it behaves in extreme cases. The average sample number function is highly predictable when the true parameter is exactly equal to either the null hypothesis or the alternative hypothesis. Why does this matter? Because it shows the efficiency of the sequential test. When the true parameter exactly matches the null hypothesis, the data we collect will consistently and strongly point in that direction. The cumulative sum moves rapidly toward the lower boundary, terminating the test very quickly. The exact same logic applies when the true parameter matches the alternative hypothesis. The sum races toward the upper boundary. At these extremes, the sequential test is highly decisive and requires far fewer samples than a traditional fixed sample test. Before we move on, let us see this with a concrete example. Suppose we are testing the mean of a normal distribution where the variance is known to be 1. Our null hypothesis is that the true mean is 0, and our alternative is that the true mean is 1. We want to control our error rates, setting both the false positive and false negative probabilities to 0.05. Our goal is to find the expected sample size if the null hypothesis is actually true. First, we must calculate our stopping boundaries. The upper boundary A represents the threshold to reject the null hypothesis, which calculates to 19. The lower boundary B represents the threshold to accept the null hypothesis, which comes out to approximately 0.0526. Continuing with our example, we now need to find the expected value of the log likelihood ratio, assuming the null hypothesis is true. For a normal distribution with a known variance, this has a standard derived formula. This formula calculates the expected evidence per step. The numerator is the squared difference between the two hypothesized means, and the denominator is twice the variance. Notice the negative sign in front. This indicates that on average, the evidence will push the cumulative sum downward toward the lower boundary. This makes perfect sense because we are assuming the null hypothesis is true. By substituting our specific values into the equation, we find that the expected value of a single step is negative 0.5. Now we have all the pieces to calculate the final average sample number. When the null hypothesis is true, the probability of accepting it is approximately 1, meaning we are almost certain to hit the lower boundary. We substitute our probability, our lower boundary, and our expected step size into the main formula. The term for the upper boundary disappears because it is multiplied by 0. We calculate the natural logarithm of 0.0526 and divide it by negative 0.5. The final result is approximately 5.89. Physically, this means we expect to test an average of about 6 items before making a decision. A traditional fixed test would require 11 samples, proving this sequential method saves significant resources. So, we have seen how efficient the test is at the extremes. This brings us to the worst case scenario, the indifference point. While the test is fast when the truth aligns with our hypotheses, it struggles when the true parameter lies somewhere in between. There is a specific value where the expected value of the log likelihood ratio is exactly 0. At this indifference point, each observation, on average, provides 0 net evidence toward either hypothesis. Because of this, the cumulative sum wanders aimlessly up and down. It takes a very long time to hit either the upper or lower boundary. If we plug 0 into our standard formula's denominator, we get a mathematically undefined division by 0, which means we need a new approach. To solve the division by 0 issue at the indifference point, mathematicians use a calculus technique called L'Hopital's rule. This results in a special formula used exclusively to find the maximum average sample number. The numerator is the product of the natural logarithms of the two stopping boundaries, with a negative sign to ensure a positive result, since the natural log of b is typically negative. The denominator is the expected value of the squared log likelihood ratio. Because the mean is 0 at this point, this term is exactly equivalent to the variance of the step size. In simple terms, when the test is completely confused, the number of steps it takes depends entirely on how widely the individual pieces of evidence fluctuate. Wider boundaries will also increase this maximum sample size. Now that we have formulas for both the extremes and the indifference point, let us look at this visually. Here we see the typical average sample number function curve. The horizontal axis represents the true parameter and the vertical axis is the expected sample size. Notice how the curve dips to its lowest points exactly at the null and alternative hypotheses. At these points, the test is highly decisive and finishes quickly. However, in the middle region between these 2 points, the curve swells upward, reaching its highest peak. This peak is the maximum average sample number, occurring exactly at the indifference point where the data looks equally likely under both hypotheses. This visual perfectly captures the worst-case scenario for our sequential test's duration. Let us return to our normal distribution example to calculate this worst-case scenario. We want to find the maximum average sample number, which occurs at the indifference point. For a normal distribution, this point happens exactly halfway between the two hypothesized means, which in our case is 0.5. Because the expected step size is 0 here, we must use our special maximum formula. First, we need the expected value of the squared log likelihood ratio, which acts as our variance. The formula for this is simply the squared difference between the alternative and null means divided by the variance of the distribution. Substituting our known values of 1 and 0, we find that the variance of our step size is exactly 1. Continuing with our calculation, we now plug this variance along with our previously calculated boundaries into the special maximum formula. We substitute 19 for A and 0.0526 for B. We calculate the natural logarithms, which give us approximately 2.944 and negative 2.944. Multiplying these together with the negative sign in front ensures our final sample size is positive. The result is approximately 8.67. Practically, this means that in the absolute worst-case scenario, where the true mean is exactly halfway between our hypotheses, we will need to test an average of about 9 items. Even at its most confused, the sequential test is still more efficient than the fixed sample test of 11 items. We have covered a lot of ground today, so let us review the key takeaways. First, the average sample number function is a powerful mathematical tool that predicts how long a sequential test will take based on the true state of the world. Second, we saw that sequential tests are incredibly efficient, requiring very small sample sizes when the truth strongly aligns with either the null or alternative hypothesis. Third, we must always be aware of the indifference point, where the test struggles to decide and the required sample size reaches its maximum peak. By understanding and calculating the ASN, statisticians and engineers can confidently design experiments that save valuable time, money, and resources without sacrificing accuracy. You now have a solid understanding of the average sample number function.